Hello everyone, here is Khaled Omar, and in this video I'm going to demonstrate multi-protocol label switching or MPLS. So the contents of this video, we will discuss 2 out of 3 topics. We will start by introduction to MPLS, then we will move to discussing MPLS Unicast IP forwarding, and in a later video I will discuss MPLS VPNs. So in this video I'm going to discuss only the first two contents. So let's start. We will start by introduction to MPLS. What's MPLS as a definition? Actually, MPLS is a routing technique that is used by service providers to connect an enterprise sites. This is the definition of MPLS in its most basic form. So we have here service provider. We have here service provider in this cloud. It has MPLS network, and we have enterprise one that has 4 sites, site A, B, C, and D. They are interconnected to each other through the service provider MPLS cloud. So as a definition, MPLS is a routing technique that will be used inside the service provider network to connect all these sites that belongs to the same enterprise. Another definition that can be used, or another application for MPLS, which is called Mpls Vpn. So as a definition for this Mpls Vpn, it's an application that is used by service providers to connect multiple enterprises sites. So in this case, we have more than one enterprise, enterprise 1 and enterprise 2. Each enterprise has 2 sites, site A and site B for enterprise 1, and site A and site B for enterprise 2. Enterprise 1, the 2 sites of enterprise 1 are connected to each other through the MPLS cloud using MPLS VPN, and enterprise 2 sites, site A and site B, are connected to each other through the MPLS VPN network. So we use MPLS for studying its meaning as a routing technique. Then as an application, we will discuss MPLS VPN, and I will demonstrate it in another video. So we will discuss in this video only MPLS Unicast IP forwarding. And as a note, MPLS includes 2 modes of MPLS: frame mode MPLS and cell mode MPLS. And in this video, I'm going to discuss only frame mode MPLS. So let's start discussing MPLS Unicast IP forwarding. Let's start. So MPLS Unicast IP forwarding logic forwards IP packets. Let me use the highlighter, the pen. It forwards IP packets based on labels. What this means? It means that MPLS uses a different routing technique other than the traditional routing of IP packets. Usually when we use routing protocols, we forward packets based on the destination IP address resides in the IP header, whether it's an IPv4 address header or an IPv6 header. But when we use MPLS, the forwarding is totally different. It uses the labels. Actually, MPLS Unicast IP forwarding does not provide any significant advantages by itself. So why we are discussing it here? We are discussing it because many applications such as MPLS VPNs and MPLS traffic engineering use MPLS Unicast IP forwarding as one part of the MPLS network. What this means? It means we are not using MPLS Unicast IP forwarding in today's networks, but applications of MPLS uses MPLS Unicast IP forwarding as one part of its network. So, to understand MPLS, you need to understand MPLS in its most basic form, which is MPLS Unicast IP forwarding. Actually, MPLS to work, it has something like prerequisites. So what are these prerequisites? It requires the normal routing protocols, such as IGPs and EGP. And examples of IGPs, all of you knows, OSPF, EIGRP, REB, and intermediate system. And by definition, IGPs are routing protocols that are used inside the same autonomous system or that belongs to an organization. But between different autonomous systems, we are using EGP. So EGP is a routing protocol that is used between different autonomous systems. An example of EGP, we have only one routing protocol, which is BGP. So to let MPLS works, it requires the use of these routing protocols in addition to the label distribution protocol, LDP. Why to use LDP? To learn labels, assign those labels to particular destination IP prefixes, and build the MPLS for the forwarding tables. Later on, we will know what are the MPLS forwarding tables and how LDP works besides the routing protocols. So some terms are used by MPLS, and we will start by defining the MPLS router. What is an MPLS router? Actually, it is a router that injects or insert, sometimes we call it push a label, swap labels, remove or pop a label, or forward packets based on their labels. This is called an MPLS router. Another keyword that's used for MPLS routers, which is label switch routers. So when we say label switch router, we mean MPLS router. So in this slide, it shows the two types of routers that are used inside the MPLS cloud, and one type of router used at the customer side. So we have here at the enterprise side or the customer side, customer edge, and here also we have customer edge. It's a router that resides at the edge of the enterprise network as a definition. Then inside the MPLS cloud that belongs to the service provider, we have only two types: provider edge, like PE1 and PE2, and provider. So we have three MPLS terms. Customer edge, its definition is a router that has no awareness of MPLS. This router resides at the customer site, at the edge of the customer site. It has no awareness of MPLS. The second term, provider edge, as a definition, it's a router that has awareness of MPLS and resides at the edge of the provider network. So any LSR or MPLS router that resides at the edge of the provider network is called provider edge. The third term, provider, is a router that has awareness of MPLS and resides completely inside the provider network, not at the edge. So these three terms are used inside and outside the MPLS, or when we use MPLS. So let's have an overview of how MPLS works. We will consider that we have Enterprise 1 with two sites, Site A and Site B. These two sites, let's say we have host A at Site A and host B at Site B. We will consider that there is reachability between the two hosts. It means that host A can reach host B through the MPLS network. But here we are going to discuss only how MPLS works. First of all, the circles with numbers represents the steps. So let's start by step 1. When the host generate the frame and send this frame that contains the IP packet, but we will not think about the layer 2 right now. We will think only about the layer 3, the IP header, the IP packet. Host A sends the IP packet to customer edge 1, whether it's default gateway or a router in the network. Eventually, the packet that is assigned to host B should go to customer edge 1. Customer edge 1 will receive the IP packet unlabeled. Yes, normally, there is no MPLS at the customer side. So, customer edge 1 will use the normal routing using the destination IP address that exists or resides at the IP header and find the entry at the IP routing table that matches this destination prefix, and based on this it can forward the packet unlabeled. Let's think that it decides to forward the packet through this interface to BE1. The packet in step 2 is sent unlabeled because customer edge 1 has no awareness of MPLS. Now BE1, the provider edge 1, received the IP packet unlabeled. Now the packet will enter the MPLS cloud. So BE1, without more details, because details will come next in this video, BE1 will decide that it should should attach a label 10, number 10, to the IP packet and send the labeled packet outside this interface to provider 1. Now provider 1 will receive the labeled packet. What it will do? It will do swapping for the labels. Swap label number 10 to label number 15 and attach the new label to the IP packet header and send the labeled packet according to the MPLS forwarding tables through this outside this interface, out of this interface to provider edge 2. Now provider edge 2 will receive the labeled packet with label number 15 and it will decide that this label should be removed in step 5 and send unlabeled packet to customer edge 2. So the packets that will be sent from BE2 to CE2 is unlabeled packet because CE2 as definition it has no awareness of MPLS, so it shouldn't receive a labeled packet. Once CE2 receives the unlabeled packet, normally it will check the destination IP address, compare it to the IP routing table, make a routing decision, decides it should forward the unlabeled packet, the normal packet, out of this interface to host B. Actually, this is an overview. More details will come in the next slides with more details. So some definitions are used as well for the MPLS routers. But they are more detailed definitions for the MPLS routers or the LSRs. First, we have Edge LSR. Its a definition. An LSR at the edge of the MPLS network that processes both labeled and unlabeled IP packets. This is something like provider edge, but more details will come next. This edge label switch router has two types: Ingress edge label switch router and Egress edge label switch router. So to define the Ingress edge label switch router is a label switch router that receives unlabeled packet. So it receives unlabeled packet and inserts or push or inject a label in front of the IP header before forwarding the packet. As an example from the previous diagram or topology, we have BE1. So BE1 is considered as Ingress Edge Label Switch Router because it received an unlabeled packet from CE1 and it injected label 10 to the IP header and forwarded the packet, the labeled packet. Another definition, another type for the Edge Label Switch Router is the Egress Edge Label Switch Router. This Egress Edge Label Switch Router is a label switch router that receives a labeled packet and removes or pops the label from the IP header before forwarding the packet. As an example, from the previous topology, we have BE2. BE2 received a labeled packet and removed the label and sent unlabeled packet to customer edge 2. So BE1 acts as an Ingress edge label switch router. BE2 acts as an Egress edge label switch router. And BE1 acts as a normal label switch router. And as we said earlier, label switch router means an MPLS router. Sorry. So what are the forwarding tables used by MPLS? Actually, MPLS uses two types of tables, forwarding tables. The first table is called CIF, forwarding information base, and the second table called MPLS, label forwarding information base. Here's the acronyms and what it stands for. CIF is Cisco Express Forwarding, FIB, Forwarding Information Base, MPLS, Multi-Protocol Label Switching, LFIB, Label Forwarding Information Base. So what are CIF FIB and MPLS LFIB? By definition, CIF Forwarding Information Base is a table that is used for forwarding unlabeled packets. Based on what? Based on the destination IP address. So what is MPLS LFIB? MPLS LFIB is a table that is used for forwarding labeled packets based on labels, the labels attached to the IP packets. So to forward packets inside the MPLS network, LSRs or MPLS routers uses both CIF FIB and the MPLS LFIB. We will explain this in details in coming slides. But you should know that there are two types of tables, CIF FIB and MPLS LFIB. Sometimes it's referred to only FIB and LFIB. So let's see how the forwarding process works with MPLS. From the previous example or the previous topology, CE1 sent unlabeled packet to provider edge 1. So how PE1 will react? It received unlabeled IP packet. Once it receives an IP labeled packet, it will check the safe FIP that resides inside PE1. So what are the elements of the safe forwarding information base? First, there is the prefix that lists all the prefixes learned to PE1. Second is the action, what to do when PE1 receives a packet unlabeled that is destined to this specific prefix, and what is the label that should be pushed or injected to the IP packet, and through which interface the packet should be forwarded. This is called the safe FIP. So when a provider edge receives an unlabeled packet, it will check the safe FIP table, find the matching entry for that prefix inside the unlabeled packet, and then take the action, which is push or inject or insert a label with value decimal value 10, and send this packet, the labeled packet, out of serial 001. So this is how PE1 will react to the unlabeled packet. Once PE1 decided to send the labeled packet out of serial 001, the packet will be received by P1, provider 1. So P1 received a labeled packet. So which table it should check? It should check its MPLS label forwarding information base. Why? Why BE1 checked safe FIP and B1 checked MPLS LFIP? Simply because BE1 received unlabeled packet. So when an MPLS router or LSR receives unlabeled packet, it should checks the FIP table. When an MPLS router or LSR receives a labeled packet, it should check its LFIP table. So now B1 received a labeled packet, so it decided it will check its LFIP table. What this table has, it say in label. So when you receive a packet with MPLS header, and in this MPLS header a label 10, take this action, swap. Swap what? Swap the label. So what is the new value of the label? 15. What should I do? I should forward this new labeled IP packet out of serial 010. So P1 will receive a labeled packet with label 10, checks the LFIP, take the action, swapping to value 15, send outside of serial 010. Now BE2 will receive a labeled packet. What should it do? It should check its MPLS LFIP, label forwarding information base. And when a matching entry found for incoming label 15, the action should be bob or remove. So PE2 should remove this label. This number 15 should be removed, the complete MPLS header, including the label. And later on we will discuss the MPLS header. So out which, what is the value of the out label? Of course, I'm removing. So I'm not swapping. So removing means I will not add another label. So this value is not available because the packets will be exit unlabeled. Once the router here First of all, it will be out of interface fast Ethernet 01, and it will be sent to CE2 unlabeled, and then it will forward the packet normally. So, as a note here, all label switch routers, PE1, provider edge 1, provider 1, and provider edge 2, all of them have both CEF forwarding information base table and MPLS label forwarding information base. But which one to use based on the received packet? If the packet received is unlabeled, use the FIP. If the received packet is labeled, use the label forwarding information base. So what is the MPLS header? Actually, the MPLS header is not very large. It's only 4 bytes header. The 20 bits of it are for the label field. The next 3 bits are called experimental or EXP. The next 1 bit is called bottom of stack. The next 8 bits are called time to live. So the MPLS header have only 4 fields, and it is 4 bytes length header. So what are those 4 fields? Starting by the label its length is 20, and it contains the label number, and in the output of the show commands it is represented in decimal value, 5, 10, 200, 500, etc. The next field is called experimental or EXP. Its length is 3 bits, and it is a marking field for quality of service. So it allow for quality of service marking for the 8 values that can exist on the EXP field, and it can be used for queuing. So the next bit is called bottom of stack. It's only 1 bit length. It acts as a flag. When it is set to 1, actually it will not be explained in this video. It will be explained more when discussing MPLS VPNs. But when this bit is set to 1, it means that this is the label immediately preceding the IP header. So in case there are multiple labels attached to the IP packet, when this bit is set to 1, it means that this is the label immediately preceding the IP header. When it is not set, it means that this is the label not immediately preceding the IP header. The next field is time to live, and it is 8 bits length, and it is used to identify looping packets and to trace the route, simply like the IPTTL or the TTL field that is used inside the IP header. Now we will discuss the protocol used by MPLS that is used in addition to the routing protocols, which is called Label Distribution Protocol or LDP. Actually, for pure IP routing to work using the CEF forwarding information base, router must use control plane protocols, such as routing protocols, EIGRP, OSPF, RIP, etc., to build the IP routing table, and then from the IP routing table you can build the CEF FIP. Similarly, for MPLS forwarding to work, MPLS routers must use control plane protocols, such as LDP or Label Distribution Protocol. There is another version before LDP. It's called its earliest pre-standard version. It's something like LDP, but it was used earlier, called TDP or Tag Distribution Protocol. But recently we are using the standard LDP. So this protocol is used to learn which MPLS labels to use to reach each IP prefix. And then when it attach a label to each learned IP prefix, it then update the CEF FIP and update the MPLS LFIP with the correct labels. Similarly or simply, LDP advertises labels for each prefix listed in the routing table. This label is called for the advertising router as a local label. What this means, if a router, MPLS router or LSR, received an IP prefix update, learned a new IP prefix. So what the MPLS router should do, it should attach a label or for each learned IP prefix. So each IP prefix listed in the IP routing table, it should attach to it a label. This label called for the advertising router a local label. So from the previous example, imagine with me, BE2 learned about prefix from host B, let's say 10.3.3.0. So once it learns this IP prefix, it will attach or assign a label to this IP prefix, and this label is called a local label. Later on, label switch routers will use the LDP, the label distribution protocol, to send messages to the neighbors. And these neighbors are called LDP neighbors. So there is a new kind of neighborship that exists in MPLS that LDP use called LDP neighbors. And these messages lists an IP prefix and the corresponding label. So once the MPLS router assign a local label for the learned IP prefix, it will send a message to all the LDP neighbors, and this message lists the IP prefix and the corresponding label, which is the local label used by the advertising router. So by advertising an IP prefix and label, these are the message contents, IP prefix and label. The label switch router is essentially saying the advertising router, if you want to send packets to this IP prefix, send them to me with the MPLS label listed in the LDP update message. So any router advertise an update with an IP prefix and label, it says to the LDP neighbor, if you want to send packets to this IP prefix, send them to me with the MPLS label listed in the LDP update message. Second thing related to the LDP, the MPLS routers or LSRs must use a routing protocol. Why? To learn routes to trigger the LDP process of advertising labels. How this works, all of us knows the IGP, EIGRP, OSPF, etc. learns routes and it chooses the best of them and prevent loops of learned updates, etc. So LDP must, MPLS routers must use a routing protocol to learn routes to trigger the LDP process of advertising labels. Actually, to understand the complete process, you need to understand a bit more about what occurs inside an MPLS router. What each MPLS router do when it receives IP prefix label binding. In particular, all these updates are stored in a data structure called the MPLS Label Information Base or LIP. So what is label information base? Actually, all MPLS routers stores labels and related information. What are related information? The outgoing interface, the next hop IP. This type of information, in addition to the labels, are stored inside a data structure called label information base. So all the labels and the related information comes from the LDB neighbors are stored inside the LIB on each MPLS router. So simply the LIB essentially holds all the labels and the related information learned from the LDB neighbors. Any label will come from an LDB neighbor will be stored inside the LIB. Why? To make processing on this receiving label and choose which one is the best based on things that we will discuss later. And actually we can say it right now. However, each MPLS router must choose the best label because it received a lot of labels from different LDB neighbors. So which one is best for this specific IP prefix? These labels should be stored first in a data structure. Then the MPLS router must choose the best label and outgoing interface to use, then populate that information into the local LFIB and FIB. As a result of these procedures, the forwarding information base and the label forwarding information base contains all labels known to the MPLS router. And these labels represents the best labels. So to make a decision about the best label to use, MPLS routers rely on the routing protocol's decision about the best route. So when an MPLS router, think about this. MPLS router received labels for a specific IP prefix from LDB neighbors. It doesn't know which one is the best. So MPLS routers or LSRs relies on the routing protocol used because the routing protocol knows which is the best path to this specific prefix. So this decision will be taken by or relying on the routing protocol's decision about the best route, and this route with this specific label will be the best label to use. Also, by relying on the routing protocol, the label switch routers can take advantage of the routing protocol's loop prevention, because a router or MPLS router can receive many labels for a specific prefix, IP prefix, and this can make a loop in some way. So by relying on the routing protocol used inside the MPLS network, we can take the advantage of loop prevention mechanism or feature that is used by the routing protocol. And react to the routing protocol's choice for new routes when the convergence occurs. So simply, LDB use LIB to store labels inside an MPLS router and rely on the routing protocol to choose the best label for a specific IP prefix and use the feature used by the routing protocol, such features like loop prevention and conversions. When conversion occurs, it can converge to another label based on the route that will be chosen by the IGP. So here is an example or a simple example actually for how label distribution protocol works and label information base works. Let's say we have enterprise 1 with two sites, site A and site B, and now site B needs to advertise this IP prefix or this subnet. So simply CE2 will advertise this IP prefix through a routing protocol, and we will discuss what are the routing protocols that we are going to use outside and inside the MPLS cloud. And once BE2 will receives these updates about 10.3.3.0/24, it will assign it a label. Let's say label 15. This label is called local label. Once it assigns a label for this specific prefix through LDB, BE2, first of all, BE2 and B1 has LDB neighborship, and BE2 and B2 has LDB neighborship. So once this neighborship is up, the next are updates. So BE2 will send the label IP prefix binding to B1 and B2. What this updates contains? It contains the local label chosen by BE2 and the IP prefix 10.3.3.0/24. This is the update that will be sent to P1 and B2. Now, let's think about P1. B1 received an update message from BE2 with incoming label 15 and IP prefix 10.3.3.0/24. What should B1 do? It will assign a new label for this learned IP prefix other than the incoming one, and we'll call it a local label. How to choose this label number? Simply, B1 will check which label that is not used and assign it to this IP prefix. So let's say it assigned a local label 10 to the IP prefix 10.3.0/24. Once it assigns a local label to this learned IP prefix, it will advertise this update to the other LDB neighbors. Let's think that there is a link between B1 and B2. So B1 will send this update to B2 with label 10 and IP prefix 10.3.3.0/24. So B2 will receive an update here and an update here for the same IP prefix, but with two different labels. Here comes with label 10 and here comes with label 15. What B2 will do? Simply, it will store this learned information, labels information, inside the label information base, the data structure, which is called label information base. And then, based on the IGB used, it will determine which one is the best label for this specific prefix, and simply update the safe FIB and the MPLS LFIB. Now, or similarly, BE1 will receive update from B1 and update from B2. What is the update that will be sent by B2? Simply, it will search for, check its labels, unassigned labels, or the label numbers that are not used by B2, and it will assign this label number to this specific IP prefix. Let's say it assigned 20 for this specific IP prefix. So B2 will send an update message to BE1 to this specific prefix with label 20, and B1 will send an update message with label number 10 to the same prefix, IP prefix. Now B1 will do the same as B2, will store these update messages inside the label information base, its label information base, and start choose which one is best and update the CEF FIP and the MPLS LFIP. What this update, let's go back to BE2. What this update means, it means it tells, let's think about this one, this update message that was sent from BE2 to BE1. Actually, BE2 tells B1, if you want to go to this IP prefix 10.3.3.0, insert label number 15. This is how LDP works. Each router assign a local label for the learned IP prefix and teach the LDP neighbors how to send the IP packet to that specific prefix by pushing the learned label from the neighboring LDP neighbor. So when B1 will start to forward a packet for 10.3.3.0, it will insert label 15 and send it to BE2, sorry. And BE2, as long as it learned from CE2 with no labels and there is no LDP neighborship, it will learn that this IP prefix, when I receive a packet labeled with 15, destined for this IP prefix 10.3.3.0/24, I should remove the label and send it to CE2. Simply, this is how it works. So there is something called label switched bus, or LSB. What is this label switched bus? It is the combined set of labels that can be used to forward the packet correctly to the destination. What means of the combined set of labels? It means from the first provider edge. If, for example, site A or CE1 is sending a packet to 10.3.3.0, what are the combined set of labels that will be inserted to the IP packet through the whole path to the destination? If P1 will choose the path to P1, then the first will be 10. Next is 15. So in this example, the label switched path is 10, 15. This is called the combined set of labels that can be used to forward the packet correctly to the destination. Is there any more labels in the road or in the path? No, because BE2 will remove the label. So only these two labels will be used, considering that the path will be through B1 to BE2. And this path was chosen based on or relying on the IGP. Then let's discuss something related to LDP. How LDP works. First of all, label distribution protocol uses a hello feature or hello messages to discover LDP neighbors and to determine to what IP address the TCP connection should be made. Actually, there are two types of connections. Connection for initializing or establishing the neighborship through the hello messages, and there are updates once the neighborship is accomplished or established. So LDP multicasts the hello messages that are used to perform the LDP neighborship to the multicast address 224.0.0.2 using UDP port 646 for LDP. If you are using TDP, it uses a different UDP port, which is port 711. So LDP uses hello messages destined for a multicast address 224.0.0.2 using layer 4 protocol UDP and port 646 for LDP. Once the neighborship is established, updates can be sent using TCP and the same port number. But let's think about the hello messages that are exchanged between label switch routers to establish the LDP neighborship. The hello messages lists each label switch router's label ID. So each label switch router should have LID or LDP ID, label distribution protocol identification. This LID consists of a 32-bit dotted decimal. Sorry. And this label LDP ID has a 2-byte label space number. Actually, this number is always 0 for frame mode MPLS. So for frame mode MPLS, the label space number is 0. Don't think about this. Think about the 32-bit dotted decimal number, which represents the LID or LDP ID. Also, each LSR can optionally list a transport address in the hello message that is sent to the other LSR before establishing the LDP neighborship. And this transport address is the IP address that the LSR wants to use for any LDP TCP connection that will come in the future. If you didn't configure this transport address that will be used, the LDP ID will be used instead. So if an LSR does not advertise a transport address, other label switch routers will use the IP address of the LDP ID for the TCP connections. So optionally, you can configure the transport address or not to configure it. If you will, it will be used for the TCP connections. If it will not be configured, the other LSRs will use the LDP ID for address for the TCP connection. So after discovering LDP neighbors through LDP hello messages, those LDP neighbors form a TCP connection to each neighbor, again using port 646 for LDP, and if it is TDP, tag distribution protocol, it uses TCP port 711 to start the communication between the two neighbors and send and receive updates. They are sending and receive updates through the TCP connection that uses port 646. Because the TCP connection uses unicast addresses, not like the hello messages. The hello messages uses multicast address, as we mentioned in the previous slide. But when the neighborship is established, a TCP connection will be performed between the two neighbors, and this TCP connection uses unicast address. This address either the neighbor's advertised transport address or the IP address in the LDP ID. And remember that these addresses, whether the transport address or the IP address in the label ID, LDP ID, sorry, must be reachable according to the IP routing table. So if you are using IGP, you should advertise these addresses to other neighbors so a TCP connection can be established. After a TCP connection is up, each label switch router or LDP neighbor advertises all its bindings of local labels and IP prefixes. So each LSR or LDP neighbor send all the known local labels and IP prefix bindings to the LDP neighbors so they can learn about this prefix and can learn about the label that will be used when sending IP packets to this neighbor. Actually, Cisco routers chooses the IP address of the LDP ID just like the OSPF router ID, starting by the 3 steps, and we will explain them in this slide. So as a summary for LDP, LDP uses transport protocols. For hellos, it uses UDP. For updates, it uses TCP. And the use port numbers by LDP. If you are using LDP, it will be port number 646. If you are using TDP, it will be 711. Usually it will be 646. Most MPLS networks uses the label distribution protocol. So the hello messages, this destination address is the multicast address 224.0.0.2. So when there are two neighbors, LDP neighbors, who initiates the TCP connection? Actually, the LSR or the LDP neighbor with the highest LDP ID. This one will initiate the TCP connection. So what is the TCP connection uses this address? What is the address used by the TCP connection? First, transport IP address if it is configured, because we said it's optionally. It's an option. If not configured, then the LDP ID will be used for the TCP connection if no transport address is configured. Last thing, how the LDP ID determination, what are the LDP ID determination rules? As we mentioned, as OSPF, for example, it starts by the configured LDP ID. Then if there is no configured LDP ID, it uses the highest IP address of an up loopback interface when LDP comes up. If no loopback interface is in up state, it will use the highest IP address of an up non-loopback interface when LDP comes up. Simply like OSPF. Now let's have this example and we will start to do the configuration. But first of all, let me explain a little bit about what we are going to do for an example for the MPLS Unicast IP forwarding. Let's assume that we have one enterprise 1, with two sites, site A and site B, who are interconnected to each other through service provider MPLS Cloud. We need to advertise this subnet or IP prefix from site B to site A through the MPLS Cloud. So let's start the configuration and we will check all the related command outputs related to MPLS configuration. So let's start the configuration. Let's open GNS. We will do exactly the same topology as this one. So let's start by 6 routers. 1, 2, 3, 4, 5, and 6. We will start calling them. Let's call this customer edge 1 and this provider edge 1, this provider 1, provider 2, provider edge 2, and eventually customer edge 2. Let's move the names, the host names inside each router. Then let's use this cloud symbol. Okay. And for each site of the enterprise, we will use this symbol. Let's give it a color. And choose another color here. Let's choose the same color here because they are belonging to the same autonomous system. So let's check how the interfaces are connected through the last slide. 20 to 20. 21 to 21. 22 to 20. 20 to 20. 21 to 21. And then 22 to 20. Is there something between P1? Yes, between P1 and P2. Serial 22. Serial 22. So now let's mention all these interfaces because it will simplify our topology for us later. 20, 20, 21, 21, 20, 220. I hope I'm not wrong as this one. 2020, 2220. I'm starting from scratch, so you can know what's going on from the beginning because there are steps of configuration that we will follow, so you should be aware with us or with me. Serial 21, 21, 22, and 20. Let's go like that. I think they are the same as this example. So let's write down the IP addresses of each link. 20.1.10/30. 30.1.1.0/30, right? Yes. 40.1.1.0/30 for this. 50.1.1.0/30 for this link. 60.1.1.0 for this link. and 70 for the link between P1 and P2, and 80 for this link. Yes. What are the LDB ID that we are going to use? For PE1 we will use 1.1.1.1, and for P1 we will use 2.2.2.2. For B2, one moment, let's say 3.0.3.3, and 4.4.4.4. Which one for which one? 1, 2, 3, 4. 1, 2, 3, 4. This, I just want to make everything clear for you. Enterprise 1 with ESN 100. Same also here, there, inside B. Let's say this side A. And this is side B. And this is the MPLS cloud that belongs to the service provider with autonomous system 200. Is there something missing? I think only thing we need to add to this figure that we are going to use EIGRP with autonomous system 200 inside the MPLS cloud. And for sure we will use LDB. Let's power on these routers. Until they are powered on, let's add the subnet here that we will advertise from side B to side A, which is 10.3.3.0/24. And we will use this on Loopback interface 0. Let's wait a little bit until all routers are powered up. And we can add console for C1. Console for P1. Console for P1. B2. B2. And C2. Let me add something here to make everything clear. Put 1, dot 2, because we are using /30. Dot 1, and the subnet number is 0 at the end. So dot 1, dot 2, dot 1, dot 2, dot 1, dot 2, dot 1, dot 2. Let's check the figure. Actually I'm not writing it, so let's use whatever we want here. So dot 1, dot 2, dot 1, dot 2, So let's start configuring the interface's IP addresses for each router, starting by CE1. Let's move to PE1. Let's move to P1. Configure 3 interfaces. I think I forgot one interface here. 2/2/2/2. Alright, let's back to P1. Press serial 2/2. Let's move to B2. Well, what I'm doing is configuring IP addresses for each serial interface. Let's move to BE2. Let's move to CE2 or customer edge 2. And configure loopback 0 for the subnet we are going to advertise from site B to site A. IP address 10.3.3. Let's say 50 255.255.255.0. Now we configured all the interfaces IP addresses. So what's next? Next we will configure the IGB inside the MPLS cloud. But before we configure the EIGRP, let's configure the loopback interfaces for all the MPLS routers that will be used later as LDBID. So simply, or let's leave this when we configure MPLS completely. So let's start by configuring the IGB, which is EIGRP for PE1. So we will say router EIGRP 200. We will choose specific network commands to enable their interface. So we'll start by 30.1.1.0, 0.0.0.3. Enter. Network 40.1.1.0, 0 wildcard mask 0.0.0.3, and that's it. Then let's move to B1. Router EIGRP 200, network 30.1.1.0, 0.0.0.3, and 70, and 50. Okay, let's move to another router, B2. What I'm doing is enabling EIGRP on the interfaces inside the MPLS cloud. But remember, I'm not enabling EIGRP on this interface serial 20 of PE1 because it is connected to another router in a different autonomous system. And by definition, IGB is a routing protocol that is used inside the autonomous system. If there are two different autonomous systems are connected to each other, we can use EGB, which is BGB. So now we configured B2, we enable neighborship. Let's move to PE2, EIGRB, sorry, router, EIGRB 200, network 50.1.1.0, and 60 only. Now what's next? Because BGB MPLS relies on the routing protocols, we will configure IGB inside the MPLS cloud, and we will configure BGB between BE2, BE1 and CE1, and BE2 and CE2. We will use only eBGB here. We will not configure iBGB inside the MPLS cloud. So let's start by CE1. router BGP 100 and neighbor 20.1.1.2 remote autonomous system 200. Let's move to BE1. Router BGP 200, it's another autonomous system. Because for sure, enterprise is an autonomous system. Service provider cloud is a different autonomous system, and the definition of the autonomous system number is a unique number that is assigned to all devices under the control or administration of a single organization. So we cannot use the same autonomous system for the enterprise and MPLS. It doesn't make any sense. They are two different organizations under two different administrations. So we'll configure now BGP between BE1 and CE1. Neighbor 20.1.1.1 remote autonomous system 100. And we will do it later. Now the BGP neighborship is up. Let's do the same for CE2 and BE2. Let's start by CE2. Router BGP 100, because from the definition, these devices or this site belongs to enterprise 1 and it is under the administration of the same organization, so it must be assigned the same autonomous system number. So let's make a neighborship with BE2 neighbor 80.1.1.2 remote autonomous system 200 and BE2 the neighborship should come up. Yes. What we are going to do next, as I mentioned, we will not configure iBGP in the MPLS cloud. Why? Because CE1 is in autonomous system 100 and CE2 is in autonomous system 100. So there are two sites with the same autonomous system number. So BGP will use the concept of loop prevention, so the routes or the IP prefixes will not be advertised through BGP. So all what we are going to do is to advertise this subnet or IP prefix 10.3.3.0 from CE2 to BE2 via eBGP. So we will configure here router BGP 100. We are on CE2 now. So we'll say network 10.3.3.0 mask 255.255.255.0. Now we should see this subnet advertised through BGP to BE2. Let's see, show IP BGP. Yes. What should we do now? We want BE1 to learn about this route. But we said, as we mentioned, we will not use IPGP. So what we are going to do, we are going to configure redistribution from BGP to EIGRP. Let's do it. Router EIGRP 200. Redistribute BGP learned routes in autonomous system 200 with metric, let's say bandwidth 10,000, delay 100, and reliability, let's say 255. Effective bandwidth, let's say 255, and MTU 1500. Now let's check BE1 IP routing table to see if this will be learned through EIGRB when the redistribution occurred on BE2 to the EIGRB. Show IP route EIGRB. Here we go. Now BE1 learned about the subnet through EIGRB from external routing protocol, not from the same instance of IGP. So it comes from BGP from BE2. Now we want CE1 to learn about this subnet. What should we do? We should come here on PE1, redistribute what is learned on EIGRB into BGP. So CE1 will learn about this subnet through BGP, the eBGP connection between BE1 and CE1. So let's say router BGP 200. We will redistribute what is inside EIGRB 200 into BGP. Let's check CE1 if it will learn through BGP, or to be specific with eBGP. Show IP route BGP. Yes, this one. Now CE1 knows how to reach this subnet through the MPLS network. As I told you in the slides, MPLS IP Unicast forwarding does not add any value. It's just letting you to know how MPLS works, because this will be used in the applications like MPLS VPNs and traffic engineering. So now BE1 can reach 10.3.3.0, sorry, .50 source. Let's use, if we will use 20, serial 20, it will not. Exactly. To make it works, let's go to PE1, because we need to advertise through BGP the subnet between PE1 and CE1. So let's say router BGP 200 network 20.1.1.0 mask 255, sorry, 255, 255, 255, 252. Now let's try. Still not working. Let's check why. CE1 show IBGB. Okay, trace route 10.3.3.50. It goes to this router and stops. Why? We will check. From BE1, let's ping 10.3.3.50. What's the IP address I assigned to CE2 loopback interface? Show IP interface brief 10.3.3.50. And let's check PE2. Okay, first let's trace from this one to know where the packet is dropped. 10.3.3.50. There is some kind of loop. Why? Let's check. ve2 show IP root 10.3.3.0. Bing will work like that. Yes. Let's check show IB EIGRB neighbors. Yes, there are neighborship with P1 and P2. Show IB root EIGRB. The route is not advertised from BGP. But how? Let me check something. B2 should be in BGP. Yes. Let's check P1. Show IB root 10.3.3.0 through EIGRB, type external. No reachability. I think this is because we didn't advertise the subnet between BE2 and CE2. So let's go to CE2 router BGP 200 network 80.1.1.0 mask 255.255.255.252. Let's check the reachability from P1. Still same issue. P1 show IB neighbors. 3 neighbors. Show IP root has to EIGRB from external. What it learned. BGP not active. We are in P1, sorry. There are no BGP here. Let's go to BE2. First check for the configuration to know what's going on, why there is a loop. Let's check P2. EIGRB from external. Yes. 60.1.1.2. Okay, but why this advertised? So let's try to trace. It's dropped at BE2. Something is missing. Did I make all the configuration? Let me check something. Show IP interface brief. Yes. Yes. Okay. Okay. Let's go to BE1. Show running section BGB. I'm just checking why there is no reachability. Let's advertise by CE2. Okay. It exists in the routing table but not reaching. Maybe the metric I used. Let me check. But it's advertised, no problem with it. So why this one? Yes. Let's go to PE2. I'm sorry for that. And advertise what's in EIGRB into BGB. Let's check from P1. Yes, it works. Let's check from B2. Okay. Let's PE1 configure again. First of all, let's check reachability. Yes. From CE1, it will not reach because we removed the network through BGB advertisement. Exactly. So let's go to BGB and advertise the network in between. Let's check reachability. Okay, we should redistribute what is inside the BGB into EIGRB. So let's say router EIGRB 200 redistribute BGB 200 metric 10,000 100 255 255 1500. Very good, now it works. So what we did, let me explain this here. We have this side B, we have this side A, we have here the MPLS network. So we advertised through eBGB the route to from CE1 to from CE2 to BE2 via eBGB. And because we are not using iBGB, because as I said, this is autonomous system 100, so by definition we shouldn't use iBGB, and this is autonomous system 100, and this is autonomous system 200. After BE2 learned about 10.3.3.0/24, we redistributed what is learned in BGB into EIGRB, and that route was learned by BE1 through EIGRB. But the other direction, first let's continue this path. We then redistributed what is inside BGB, EIGRB into BGB. So this prefix 10.3.3.0 was learned by CE1 via eBGB. What was wrong or what was missing? We didn't configure the opposite direction. We should redistribute what is in BGB into EIGRB. So the opposite path should work. And then what is inside EIGRB should be advertised into BGB in BE2. Now the two-way pass should work. Now we've configured the IGB and the EBGB between the two autonomous system or the different autonomous system. What's next? Now we will start configuring MPLS inside the cloud provider to use the new routing technique that we will use in MPLS applications such as MPLS VPNs and MPLS traffic engineering. As you can see, there is reachability between CE1 and CE2. So why we use another routing technique? Because later on another video, we will explain MPLS VPNs, so we will know what we will have when we try to connect different sites for different enterprises. We will have a problem called overlapped private IP addresses. So let's discuss this in another video. Let's first here discuss configure MPLS, and as mentioned here, the green lines means MPLS enabled interfaces. So MPLS will not be enabled between BE1 and CE1, and MPLS will not be enabled between BE2 and CE2. So let's enable MPLS on all label switch routers, or it's called MPLS routers. So let's start by PE1, interface serial to 1. To enable MPLS, just enter MPLS IB on the interface. So let's start by BE2, serial 2/2, 2/2, MPLS IP. We will not enable MPLS on PE1 serial 20 because CE1 has no awareness of that. And MPLS should be enabled inside the MPLS cloud or the service provider cloud. Now let's move to P1. Before we move to P1 and enable MPLS, okay, let's continue, and I will tell you something why the LDB neighborship will not be established. So let's start now to configure to enable MPLS on PE1, interface serial 2.1, MPLS IP, interface serial 2.2. Actually, the LDB neighborship was performed through the highest non-loopback interface IP address. But let's continue configuration, and I will tell you something. Interface serial 2/2, MPLS IP, interface serial 2/0, MPLS IP. Let's go to another LSR, B2, sorry. (2/0), MPLS IP, interface serial 2/2, MPLS IP, interface serial 2/1, MPLS IP. Actually, there is a global configuration command that can enable MPLS on all router interfaces. Simply use MPLS IP command globally, like this, MPLS IP. This will enable MPLS on all router interfaces. So let's move to BE2 to enable MPLS. We shouldn't use the global configuration command MPLS IP on BE2 because we are not going to enable MPLS on all BE2 routers interfaces. So let's configure only enable MPLS on serial 2.0, MPLS IP, interface serial 2/1, MPLS IP. Let's set configuration. Something I should tell you before enabling MPLS, you must enable IPsef on all MPLS routers. But because it is enabled by default, so we didn't configure the command IPsef. Because if you will go to the running configuration, you will find out that IPsef is enabled by default for IP version 4. But CE1 and CE2 may or may not use Ceph because they have no awareness of MPLS. But it is mandatory for MPLS routers, LSRs, to use IPsef using Cisco routers. So what's next? We should determine on all MPLS routers the label distribution protocol. By default, it uses, let me show you something, show running. Okay, let's use LDB, and I think by default it is used. So to enable LDB on all MPLS router interfaces, use the command MPLS label protocol, and then you can find LDB and DTB. And as you can see, LDB is enabled by default, so you will not configure this command. If you want to know the complete command, MPLS label protocol LDB. If the router is using TDP by default, the tag distribution protocol, but as long as it used LDB, and as you saw here, the neighborship is already performed between the MPLS routers. So now the neighborship is established. If you want to check the neighborship, you can use the command show MPLS LDB neighbor. This is on PE1. You can see there is a neighborship with this router, and let's use instead peer IP ID. Yes, this is B1, the highest IP, the highest non-loopback, the highest up non-loopback interface, and this is B2. Let's do something here to configure the LDB ID as mentioned in the figure. Simply, we should configure loopback interface. Let's say loopback interface 0, IP address 1.1.1.255.255.255.255, exit, and use MPLS LDB router ID loopback 0 force. You see the neighborship goes down, and it will not come up right now, and I will tell you why. Let's first use this command on all other MPLS routers. Let's go to P1. Here first let's configure the interface loopback 0, IP address 2.2.2.2.255.255.255, and then this command. Let's go to B. You see the neighborship now is down. It will not come up. Let's go to P2. Why? Because this 2.2.2.2 is not advertised by EIGRB. Once we will add it to the EIGRB advertisements, or we will enable EIGRB on this loopback interface, the LDB neighborship will come up. So let's go to P2 interface loopback 0, IP address 0333 255, 255, 255, 255, and then MPLS LDB router ID loopback 0 force down. Very good. Let's go PE2. Interface loopback 0. We just want to make the LDB ID known for us, because it was before it was chosen through the 3 steps and it chose the last one. Now we are configuring loopback interface, up loopback interface, so the LDB ID will be the same as IP address of this loopback interface, just to know what we are doing. So we are in loopback 0 in BE2. Let's say IP address 4.4.4.4, 255, 255, 255, 255, exit, run the command. Very good. Now let's go to when we are in BE2 router EIGRB 200, say network 4.4.4.4 0.0.0.0. Okay, let's back to P1 router EIGRB 200 network 2.2.2.2 0.0.0.0. You see the neighborship, LDB neighborship is up with BE2. Very good. Let's go to B2 router EIGRB 200 network 3.3.3.3 0.0.0.0 up. Yes. Last one, BE1 router EIGRB 200 network 1.1.1 0.0.0.0. Yes, it's two neighborship are up. To check the neighborship on BE1, the LDB neighborship, show MPLS LDB neighbor. Now you can see that BE1 is forming LDB neighborship with P1, P2 and with P1. This is the peer LDB ID, and this is the local LDB ID used by PE1 in both neighbors. Okay, and that, as you can see, the TCP connection from BE1 to B2 uses port number 646 TCP connection for the updates or the update messages. And the uptime is 14 seconds, means it's up. And we will discuss later what are the addresses bound to peer LDB ID. These addresses related to P1 are all the IP addresses related to the interfaces connected to P1. As you can see, 30.1.1.2, 50.1.1.1, 70.1.1.1, and the loopback interface. Now, as we enabled IPsec was configured by default, we enabled MPLS on router interfaces, and we used LDB by default. It was configured by default. Now let's do something to prevent the clutter or the confusion later when we will discuss the show commands. Let's configure for each router. Let's start by BE2, sorry, to use specific range of labels that is different than from the range used by other MPLS routers. To avoid two MPLS routers uses the same label number when advertising to the LDB neighbors, so it will make confusion. So to solve this issue before it happens for you, I make this for simplicity. Use the command MPLS label range and start on BE2. For example, let's start by 100 to 199. These are the labels that will be used by BE2. Okay. It will not be active until a reload, of course, will occur. And let's save the configuration. Let's go to P1, MPLS, label, range. Let's use another range, 200 to 299. Okay, it will not be active until we do a reload. Let's go to P2. Use the same command but with different minimum and maximum label values. MPLS label range. We use ta 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 ta. Okay. Let me check in P1. We just need different range. Okay, 200, 299, 300, 399. Let's go to BE1. BE1 MPLS label range 400, 499. Do right. Let's save because we will load all these routers, so it will be active to use the new label ranges or labels range. Okay, we saved here. Let's save here. We already do it. I just want to make sure that nothing will be missing, and to be sure we can save on CE1 and on CE2. Let's make a simple reload for all these routers, like stopping and starting again, so the new labels will be active. Let's wait a moment until the router powers up, and let's discuss something here related to LDB. CE1 will advertise 10.3.3.0/24 to BE2 through BGP. Now BE2 will assign a local label to this IP prefix. Let's say 110 for this IP prefix 10.3.3.0/24. And because there is LDB neighborship between BE1 and BE2 and B1 and BE2 and B2, BE2 will advertise, will send update message with label 110 because it's the local label used at BE2 for IP prefix 10.3.3.0, 10.3.3.0/24. Now when B1 will receive this update, it will assign a local label for this IP prefix, let's say 210, and send this update message to BE1. So this will be 210 for this prefix. Now BE2 will receive the same update from the LDB neighbor BE2 like this 110 and bind it to this IP prefix, and then B2 will send this update to BE1. First of all, B2 will assign another label, let's say 310 local label to this IP prefix, and send this local label with associated or binded with the IP prefix 10.3.3.0 to BE1. Now BE1 has two update messages with two different labels to the same prefix. Which one will it choose? Based on the EIGRP routing protocol used inside the MPLS network, where these labels will be stored inside the label information base. Once one of them will be chosen as best label, PE1 will update its FIB as we mentioned in the presentation slides, and LFIB. If it received unlabeled packet from CE1, it will use the FIB and use this label when sending the IP packet. If it will choose this path, when our P1 receives this labeled packet, it will use its LFIB, and so on, as we explained in the presentation slide. Let's see all the routers here quickly. Console PE1, so it will be easy to see them all later on. By the way, now we finished the configuration of the MPLS Unicast IP forwarding, and we will just check some show commands to show you how LDP works, what is the FIB, what is the LFIB, what is the LIB, etc. So let's start by BE2. And first, let's see what are the label range used by CE2. We will want to know if it took effect or not. Very good, as we configured from 100 to 199. So what we are going to do now, we want to see what is the local label assigned by BE2 to the prefix 10.3.3.0. How we know this? Let's check this command, show MPLS LDB binding, and you can write down the subnet you are looking for and the mask 24, the prefix length. You see, BE1 received an update from PE2. I'm sorry, a little bit confused between the numbers. We are working on BE2. BE2 received an update message from CE2 through BGP, specifically through eBGP, and now BE2 learned about 10.3.3.0 by BGP. Now it will send to its LDB neighbors. First of all, it will assign a local label, and this label is 107. You see, it chose any unused number, label number, started by 107, because it can use from 100 to 199. It chose 107 and sent to this neighbor, LDB neighbor, B1 and B2, this local label in an update message. Okay, you want to make sure of this, go to P1, issue the same command, you see, for this prefix, the local binding is 206, and sent, sorry, I think something make me confused. Let me show you something about the labels in the LIB. This command is used for showing the LIB labels from all other neighbors. So this is the local label, and if you will check the LFIB on PE1, show MPLS forwarding table for 10.3.3.0 length 24. Exactly. This is BE2 sending LDB updates to P1 saying to reach this IP prefix use label 107. So B1 used the label that came from, by the way, all the labels received by B1 for the prefix 10.3.3.0. Which one is the best based on the EIGRB, and which one will be added to the label forwarding information base? This one. So this command show MPLS LDB bindings for a specific IP prefix shows the data structure which is called label information base. All the labels received for this subnet. Which one to choose based on the IGB is to choose this one and added it to the label forward information base, and we will check also the FIB, but let me finish this one. As you can see, P1 says that if you want to reach this subnet, this IP prefix, use outgoing label. By the way, if the local label came with 206 and this came from BE1, if you will look here, BE1 advertised the labeled packet with label 206 that wants to reach this IP prefix. BE1 will not look on the IP header contents. It will look on the LFIB because it received a labeled packet. So what should it do? It should do swap from 206 to 107 as the update came from BE2 and send the packet out of serial 20, which is directly connected to BE2. Now let's check B2. Let's check the label information base, show MPLS LDB bindings. If you will hit enter, it will show you all, as you can see, all the labels for each IP prefix, but it will be so long list. So let's use it specifically for the prefix, this with prefix length 24. So let's check. You see it has in the label information base 3 labels, comes from 3 different routers, 2 which is B1, and another one from BE1, and a third one from BE2. Which one is the best based on the EIGRB routing protocol? It choose this one. So if you will check the LFIB on B2, show MPLS forwarding 10.3.3.0 prefix length 24, you will find out that yes, it choose this label that comes from 4.4.4.4, which is BE2. So any incoming packet labeled with 306, automatically B2 will use this table and make swap and send the packet out of serial 21. It will not check the IP prefix. This is how the MPLS routing works. Labeled packet received, check the LFIB. Let's check BE1 to see if it will receive unlabeled packet destined for this specific subnet. So first of all, we will find two labels in the LIB for this prefix. Yes, as you can see, the local label used by BE1 for this prefix 10.3.30/24 is 406, and an update message came from 2.2.2.2 with label 206, and update message for this IP prefix came from B2 with label 306. Which one to choose? Let's check the LFIB table, and we will know which one is chosen. It choose both, because simply EIGRB, let's see, show IP root EIGRB 200. You see, where is this subnet? Yes. EIGRB simply choose these two roots for that specific prefix because they have the same administrative distance and the same metric. So that's why BE1 choose the two passes. If you want BE1 to choose only one, you can play with the, for example, the delay on the link between BE1 and B2 to make the delay higher than the delay on the link between BE1 and B1. So only one of the two labels will be preferred, will be the best, and only one entry will be added to the LFIP. So let's check where are we? Yes, on BE1. Let's check the FIB on BE1. Show IBSEF 10.3.3.0 24 without 24. So from the LIB, this LIB is data structure which has two received labels. It updated as well the FIB table 206 and 306. 206 and 306. If you will check B2, we want only one entry to be preferred over the other. Let's check the LIB table on P1. Okay, 3 labels are received from 3 different LDP neighbors, which are we are on P1. Yes, it came from B2 3.3.3.3, BE1 1.1.1.1, BE2 4.4.4.4. Which one is preferred? Let's check. Show MPLS forwarding table for prefix. It preferred the one that came to P1 with label 107. So it became its outgoing label. Because as we mentioned here, let's change this 110 to 107. And another label came from B2 with a different label, which is 306, and from PE1 with 406. So which one B1 will it choose based on the routing table? The EIGRB, the IGB, it choose this update as an outgoing interface. So the LIB received all these 3 labels and updated the LFIB with only one entry, the best one, the best label. So let's check, show IBSEF, the FIB table for 10.3.3.0. Exactly, it chose this label. this IP prefix, which is 5.1.1.2, which is BE2. To this, we just finished all the configuration, but let me show you something. One last thing. Let's summarize what we discussed. We configured IGB, EGB, MPLS, and before configuring MPLS, we used redistribution between the IGB and EGB in both sides. And then we configured MPLS. We configured LDB ID instead of the default choose one. We configured a label range for each router. Each one has a different label range to make no confusion. And we tried the commands for showing the LIB, the LDB neighbors, show MPLS LDB neighbors, and the command for showing the forward information base table, show IBSEF, and if it is for a specific subnet, type it, or simply use show IBSEF. And we used the show command to show the label forwarding information base, which is show MPLS forwarding table for a specific prefix. One last thing, let's go to CE1 and do trace. And we will see what is happening. We will see that the first hop is PE1, no labels. Then through B2 with label 306 sent from PE1 to B2. And then B2 sent a labeled packet, made a swap and sent to 107, sorry, to BE2 with label 107. And then BE2 advertised unlabeled packet to sent unlabeled packet to CE2. Let's check something on PE2. The LFIP show MPLS forwarding 10.3.3.0 24. You see on PE2, if a received labeled packet came to PE2 with label 107, the action to Bob to remove the label and send the unlabeled packet outside of serial 2/2. Why we checked the LFIB? Because the packet came to BE2 is labeled as label 107. One last command we will use on all MPLS routers, BE1, B1, B2, BE2. Why? To stop the propagation of the TTL. What is the propagation of TTL? As you can see, because TTL propagation is enabled by default on all MPLS routers, you can see all the paths. Sometimes service providers don't want the customer to learn the router IP addresses inside the MPLS network. So to do this, you have to disable MPLS TTL propagation on all label switch routers inside the service provider. Which command to use? Let's start by PE1 and copy the command to the other LSRs. Let's go to the configuration mode. The command to disable MPLS TTL propagation is no MPLS IP propagate TTL. And there are two options, forwarded and local. Forward means to prevent the customer from learning router IP address inside packets, inside the MPLS network. So forwarded means packets received from customers. So if I will do forwarded, it will choose packets received from customers only. But local are packets created by service provider routers. So if you use forwarded on all MPLS routers, let's go to P1, conf t paste B2 paste BE2. Now let's check from CE1 point of view. First of all, as you can see, the path when we did trace route has 4 hops and mentioning the labels used inside the MPLS network. If you will repeat this command, trace route, you see the MPLS cloud appeared as a single hop for the customer because we disabled MPLS TTL propagation. So only 3 hops instead of 4 hops, because inside the MPLS there are 2 hops, and when we disabled it appeared as 1 hop, so 1 hop was removed. So to this topic we come to an end to the MPLS IB unicast forwarding, and on another video we will discuss the application that will use this concept but in a different way. So if you understand this very good, you understand the application MPLS VPNs. So I hope this video is informative, and thanks for watching.